Hi everyone, it's Mrs. Giles, and today we're going to work on Day 4 notes, adding and subtracting radicals. Up here on the very top of the page, we do have about 6 warm-up problems, so if you'd like, you can hit pause, and you can try some of those warm-up problems with the multiplying and one of the dividing problems. And then once you hit play again, the answers will be up there. So go ahead and hit pause if you'd like. If not, the answers will appear shortly. All right, there we go. There's our nice warm-up problems completed. So hopefully you had a chance to try a few and check them. And as we scroll through now, we have a few things to remember about things we've done in the past with like terms in order to tie into adding and subtracting radicals. So over here in the beginning, our quick review says, what would you get when you add 3x and 4x? And if we remember, like terms simply means that you have the same variable raised to the same power, and then what we're going to add and subtract are those coefficients out in front. So if we have 3x's and we add 4x's to it, we will have a total of 7x. So take a minute, add and subtract a few like terms for me in problems B and C over there, and let's see if we can match the same answers. All right. So in letter B, hopefully you combined your like terms. They're all like terms, so we have 10 minus 4 plus 2, and it's all the coefficients that we are working with. So 10 minus 4 is 6, plus 2 gives us 8 for our total of x squareds. So they all had an x squared, so we were able to combine them all into one term. Over in letter C, if you take a look at those three terms, there are some like terms, but not all of them are like terms. We do have a 9x and a positive 3x that are like terms, and those two can be combined to give us a total of 12 x's. But then we still have this third term in the middle there, that minus 4y. It's not a like term to the 12x, so the 4y will have to stay its own term. So we simply have a binomial as our answer instead of everything combining like the first two problems into monomials. Now, if you remember how the variables work for like terms, you're in great shape on how to combine radicals by way of adding and subtracting. To be like terms, we need to have like radicals. So when we look at the first problem, the two terms say we have 3 square roots of 2, and we want to add to it 4 square roots of 2. So just like up above, when we had 3x plus 4x, we had 7x. Well, likewise here, we will have 7 square roots of 2. So we are still simply adding and subtracting the coefficients. We are not adding and subtracting the like terms underneath the radical. It's just the how many of those like terms we have. So in letter B there, we have some root 7s in our terms. If you remember, when there's no coefficient out front, it is that 1 root 7. We're going to subtract 8 root 7 from it. So 1 minus 8 gives us a total of negative 7 root 7s. They were both like terms because they both had a 7 under the radical. All right, what about letter C though? When we look at it, we have a root 6 and we have a root 3. And we have to ask ourselves, is there any way we could break down that root 6? We can, but our root 6, if we simplify a square root of 6, we will only be able to have square root of 2, square root of 3. It won't simplify. We don't have any pairs that we can take out from under the square root, so we will have to keep our 5 root 6 as a term. Likewise, we have our 8 root 3. They are not like roots, so similar to up above with having x's and y's, we have a root 6 and a root 3, so that is the best we can do in terms of combining those radicals. They are not like roots, so they cannot be considered like terms and put into one term. So our rule says when adding and subtracting radicals, the radicals must have like radicals or like radicands. The underneath part, under that square root, is what we're looking for in terms of being like radicals. If we have just a number, that's great. The numbers need to match. If we have variables under the radical, then the variables and their exponents need to match. So it's just like having like terms under a radical to be considered like radicals. All right, so let's continue on. We have a couple more problems here on the front page, so take a minute and look at those problems. Look at number 1. Decide, do you have any like terms? Hopefully as you scan through it, there are 3 terms. They're not all like terms, but we do have a few terms that we can combine. So hopefully you're noticing those root 7s. 3 root 7s in the first term, 8 root 7s in the last term. Together will give me 11 root 7s. And then our middle term, 2 root 3, is not a like radical, so x and y's stay separate terms, so will our root 7 and our root 3. Now look at number 2. When you look at those radicals and the radicand, the part underneath the radical, hopefully you're noticing something in that first term. We have a square root of 4. So a square root of 4 in the first term can be simplified. It's not a like radical with the second term, the 7 root 2, but square root of 4 itself can be simplified. It's a perfect square. So the 3 will keep, but we'll take a 2 out also from that square root of 4. And then second term, 7 root 2, can't do anything with it. 2 is a prime number. We can't break it apart any further. The first term no longer has a radical. It's simply a 6 added with a 7 root 2. It's kind of like when you had expressions before that had like a 3 added to a 5x. They both had numbers, but they weren't like terms because they didn't both have the variable x. Well, same thing here. We have two terms. They don't both have that same radical 2, so they're not considered like terms, and that's telling us that we cannot combine those terms. All right, last one here on this front page. I see a root 6 in the first term, and I know I can't simplify that because I tried to up above, so I know I'm going to have a 2 root 6 as my first term, but 54 under a square root will allow me to break it apart a little bit. So think of those times tables, think about what times what is 54, and hopefully you can come 9 times 6 is 54, and 9 is a perfect square. So we will be able to simplify a little bit before we even try to combine our like terms. So think way back to just simplifying the radicals last week, and we'll see where we're at with this. We have our 2 root 6. We're going to subtract from it, keep the 5, but the square root of 9, we can take the square root of 9, and that will give us a 3 on the outside. Let's take the square root of 6, or break it apart into any type of pairs, so we're going to leave it as a square root of 6. Now we do have a little bit of combining, a little bit of multiplying to do on the outside, so I keep my 2 root 6 for the first term. Now I have a 15 root 6 for the second term. And look at that, they are now considered like terms. Both terms have a root 6, so we can actually subtract the coefficients. The 2 and the negative 15 will make a negative 13 root 6. So hopefully things are going well. We have a couple more problems on the next page. They were called partner practice, but let's go ahead and take a look at a few of those and see where we're at. So go ahead and flip over to that next page. Similar to that last problem that we did, we do have a couple radicals in each one of these problems that we will be able to simplify. And once it's simplified, we can go ahead and see if we do have any like roots that we will be able to consider like terms and combine. So take a look at that first term, 3 root 3. 3 is a prime number, so I'm not going to be able to simplify the root 3, so we'll leave that term alone. But hopefully we're getting better at recognizing 27 as having a perfect 9. 9 times 3 is 27. So I can simplify the second term. So we'll keep the first term as is. Square root of 9 in the second term, we'll put a 3 on the outside with a square root of 3 still left behind. And now look at my terms. I have a 3 square root of 3, and I want to subtract another 3 square root of 3. So subtracting the outside numbers, 3 minus 3 would give me 0 square root of 3. But we know when we multiply anything by 0, 0 times anything will always result in a 0. All right, take a look at number 5. Number 5, we have a square root of 20, a square root of 18, and a square root of 5. So 5 is prime for the last term, so we know we're not going to be able to break that apart. But let's see what we can do with this square root of 20 and this square root of 18, and see if we can maybe simplify each of those terms separately down a little bit and get some, maybe a match with one of our square roots so we can combine some like terms. So think of perfect squares. What times what is 20? And let's try to get a perfect square in there. So hopefully you're coming up 4 times 5. There's a nice perfect square to have in the square root of 20. The 4 would make its way outside. The square root of 4 is a 2, leaving a square root of 5 behind. Multiply the original negative 2 out front with the new 2 that we brought out from the square root of 4, and we now have a negative 4 square root of 5. All right, now look at that middle term. It was a plus 2 square root of 18. So think about your factors of 18. And if there's any perfect squares that go into 18, like maybe 9 times 2. So square root of 9 is 3, so we can take a 3 on the outside. We'll leave that square root of 2 behind. The term will simplify to become a 6 square root of 2. Okay. And the last term we had already said, the minus 2 square root of 5. 5 is a prime number under that radical, so I'm not able to break it down. It's not a perfect square, so we're just going to need to keep moving that down to each level as we go along. Now that all the radicals are simplified in each term, I can go ahead and look at my terms and determine I do have a set of like terms. I have a negative 4 root 5 and a negative or minus 2 root 5. So together, negative 4 minus 2 will combine like terms to be a negative 6 root 5. And my middle term, the 6 root 2, we're just going to leave that as a separate term. It's not a like term to the others, so we'll just leave it a binomial. We have two different terms, and they're just not like terms. It's all one number if we keyed it in the calculator, but in the case of trying to put terms together, a root 5 cannot be combined with a root 2 by way of adding or subtracting. All right, last one for us to do together. Check out these square roots. We have a couple big numbers here. We have a 27 under the root, a 50, a 48, and a 128. So we'll have to take our time and try to think about what kind of perfect squares can we get as factors of each of these numbers. So 27 we just broke apart in one of the previous problems, and we said 27 is square root of 9 times 3. I have to write a little bit on the smaller side here to make this fit. The next term, square root of 50, well, we know 50 has the factors of 25 times 2, and 25 is a good perfect square for us to use. 48, let's think about our perfect squares. I know we think 24 times 2, and we think about 6 times 8, but we want a perfect square in there, so keep thinking about it. And what if we use 16 times 3? Now, if you didn't come up with that right away, you could take the 48, go off to the side of your paper, do a number tree, and you could break apart that 48 under the square root like we had done in the past with our number trees, and look for pairs of numbers so that you can then pair them up and take them out and kind of build your perfect squares on your own. 128. That's another one I'm going to have to squish in here. I'm kind of on the edge of my paper. Square root of 64 times 2 is 128. So I'm going to stick a times 2 down here in the bottom. Sorry about that, but I ran out of room on my paper. In the next line, we'll get it cleaned up a bit. All right, so 64 times 2 is 128, and 64 is a good perfect square. So now let's go through each one of these terms and take out all these perfect squares. So I had a 3 in the first term. Square root of 9 is another 3 on the outside, and then we'll leave a 3 behind. So altogether I have 9 square root of 3 for my first term. In the second term, that square root of 25, I can take out. The square root of 25 is 5, so I originally had a minus 5. I take out a 5, and I'm going to leave behind a square root of 2. So my second term will simplify to be 25 square root of 2. Third term, we did not have a coefficient, it just had that invisible 1 there, so I still have an invisible 1. When I take out the square root of 16, 1 times that 4, the square root of 16, will make it a 4 root 3. So my third term is 4 root 3. And then my last term that's kind of squished in here, I had a 2 out in front, so that's a plus 2, multiplied by the square root of 64, so that'll be an 8. And then I still have that square root of 2 that was kind of hanging off the page there that I had to put underneath. So my last term simplifies to be a 16 square root of 2. All right, now scan across our 4 terms, and hopefully you notice we do have a couple sets of like terms. We have 2 terms that have square roots of 3. We have 2 terms that have square roots of 2. So if we go ahead and do the adding and subtracting for the coefficients of each of those like terms, we would have 9 plus 4 would give me a total of 13 square roots of 3. And negative 25 plus 16, think negative 25, positive 16 is going to give me a minus 9 square roots of 2. Now these are not like terms because they do not have the same radicand, the same value under the square root. So that is the simplest I can make it, is 13 root 3 minus 9 root 2. All right, the problems down on the bottom here are just another